All right, so we're in section 12.2 today.
What's weird about me going to a Kanye West concert? What's weird about that? He canceled it. I was so bummed. Yeah. But I'm never going to go to the Venus tour.
So we're going to talk about derivatives of vector valued functions. So we're going to start with a vector valued function. So we have r of t, and we're going to say this is r of t is I'm just going to say VVF, vector valued function. We're going to define the derivative. Just like we define the derivative of a single variable function, we're going to say r prime of t equals the limit as delta t approaches 0 of r of t plus delta t minus r of t over delta t. So that's how we're going to define our derivative. And we say that if r prime exists, we call the vector valued function differentiable. But this is like the derivative of a single variable function. This limit is our definition. It's a nice definition. We want something that we can actually work with. Before we come up with a way that we can actually take derivatives of vector valued functions, let's draw a picture of what we're talking about. So we have our axes. And we have, here's our vector r of t. And I'll draw several.
Mr. Beamer, you have two x-axes.
I have two x-axes. Is that a problem? Xi. All right. And I'm going to draw one more vector. I'll draw my other vector. All right, so this vector is r of t. This is the vector some time delta t later. So this is r of t plus delta t. And the blue vector is going to be r of t plus delta t minus r of t. So we want our derivative is the limit as delta t approaches 0 of this vector divided by our delta t. So we're getting these two vectors closer and closer and closer together. So what we can do is using the definition. We use the definition, like I said at the beginning when I said I forgot to talk about limits and continuity. We go component by component, and we apply this limit. We separate our vector into components. Component by component, we can show that the derivative is just the derivative of each component. So that gives us a way to calculate our derivative. So we separate this component by component into our x, y, z components, and then we're just taking the derivative of a single variable function for each component. So we can use the definition to show. I'm going to use one of one of the favorite terms that math people like to use. We can show, but we don't actually show it. That if R of t is f of ti plus g of t j plus h of t k, and f, g, and h are all differentiable functions, then r prime of t, we just take the derivative of each component. F prime of t I plus g prime of t j plus h prime of t. So nothing really complicated here. We just take the derivative component by component. Now what we do with the derivative is where things start getting interesting. So what I want to do next is write down some properties of the derivative of a vector value function. Because we're dealing component by component, some things are a little different than they are with single variable functions. And there are a couple of properties that are very important that will come up later that we'll use quite a bit when we do more with vector value functions. So our properties of our derivative. And nothing here should be really surprising, but there are a couple that are just a little different and a couple that are really important. So we're going to say for these properties that C is a scalar, F is differentiable, so F is just a function of a real variable. So F is differentiable. And R and U are differentiable vector value functions. So our first property, the derivative of a scalar times a vector value function is just C times R prime of t. So that one's not too surprising. Derivative of a sum is a sum of the derivatives. And we have three product rules. The derivative of a real function, f of t, times our vector value function, r of t, is just our normal product rule. The derivative of a dot product. Because our dot product commutes, the order doesn't matter. We can just use our regular, think of it as just like our regular product rule. R dot u prime plus r prime dot u. And we need to remember that we're taking the dot product. And then the derivative of a cross product. Here's where we have to be a little more careful. because the cross product does not commute. Cross product anti-commutes. We switch the order, we change the sign. So we have to take care of the order that we do these cross products. So this is going to be r cross u prime plus r prime cross u. So we have to keep the order. We have to maintain the order. And then we have a chain rule. That the derivative of r of f of t and this is just our normal chain rule, r prime of f of t times f prime of t. So a normal chain rule here. This next one is pretty important, and it will come up in several places later on in the semester. If r dot r equals a constant, equals a constant, so doesn't vary in time, then r dot r prime equals 0. So this is an important one. Just keep this one in the back of your mind. And this comes straight from this product rule. If our dot product is a constant, then r dot r prime is 0. And then the last thing we want to say about the derivatives is that if r prime equals 0, and I'll put my time in there just so we can, because we're going to be referring to the time, our parameter. R prime of t equals 0, then the curve represented by r of t has a cusp at that value of t. And another way of saying this is that r is smooth everywhere that r prime does not equal 0. So those are our properties of the derivative. The ones we'll use, they come up fairly often. And the other thing to keep in mind is with these product rules, with any of these rules, we could perform the dot product, we could perform the cross product before we take the derivative. So we don't have to do it separately. We could do it before. So this just gives us another way of working. Questions about our properties? Derivatives, vector value functions, integrals of vector value functions, not really difficult, not really new. Yeah, we will do some interesting things with derivatives and integrals of vector value functions. So all I want to do next is just go through an example of calculating a derivative of a vector value function. The thing that makes working with vector value functions a little more difficult is you end up doing everything 3 times because you have an x, y, and a z component. So you have just more to keep track of. All right, so let's look at an example. if r of t is the cosine of pi ti plus the sine of pi tj plus t squared k hat. And we're talking about this particular time t0 equals negative 1/4. So before we start, we want r prime at t0 over the magnitude of r prime at t0 and r double prime at t0 over the magnitude of r double prime at t0. So we're just going to calculate these derivatives. So first off, before we start calculating, what kind of curve is this describing? There it says it's a helix. So we get a cylinder, and our axis is the z-axis, and we have t squared k. So what is a t squared doing to our helix? So I'm stretching it. It's like I think of it as kind of like a stretched spring. So it's going to, the coils, the pieces of the helix are going to be closer together, closer to the xy plane, and as we move up, it's going to stretch out further and further. So kind of like a stretched out spring. All right. So let's calculate some derivatives. What's r prime going to be? Someone help me out here. Negative pi sine pi t. I, and our j component will help us, plus pi cosine pi t, and our k component, thank you, 2t k hat. So let's plug in, so there's our derivative. We're going to plug in t0. R prime of negative 1/4 is going to be negative pi sine negative pi fourths I hat plus pi cosine negative pi fourths j hat plus 2 times negative pi fourths k hat. Yeah, you're right, 1/4. I don't have a pi there. Thank you. And sine of negative pi fourths? Negative square root of 2 over 2. So I get, for my r prime, I get pi square root of 2 over 2. Cosine of negative pi over fourths? Square root of 2 over 2, so I get pi square root of 2 over 2. And here I get minus, and I forgot my j hat again, minus 1/2 k hat. So there's r prime at t0. and we want the magnitude, we want to divide that by the magnitude of r prime at t0. What is r prime divided by the magnitude of r prime? What does that give us? A unit vector. So we're getting a unit vector. We're getting a unit vector in the direction of r prime.
So that means a unit function.
A unit function?
Vector value function.
Well, it'd be a unit vector. It's a unit vector at t0. So it's not always. Let's see. So this would be t0. Yeah, I guess it would be. So if we wrote the general function r prime of t over the magnitude of r prime of t, we'd get a unit vector value function. All right, so let's find our magnitude. The magnitude of r prime at t0 is the square root of
You wrote r double.
pi, thank you, pi square root of 2 over 2 squared plus pi square root of 2 over 2 squared plus 1/2 squared. So I get square root of pi squared plus 1/4. And I could rewrite that as 1/2 square root of 4 pi squared plus 1. So finally, r prime at t0 over the magnitude of r prime at t0 when I divide this, my 2's are all going to cancel. So I get 1 over square root of 4 pi squared plus 1 times pi square root of 2 I hat plus pi square root of 2 j hat minus k hat. And that would be my vector r prime over the magnitude of r prime. A unit vector in the direction of r prime at time -1/4. And I think we're gonna skip going through the second derivative. Second derivative, same process. We would take the derivative of this quantity, evaluate that at t0, find the magnitude of that quantity at t0, and go through the same process. Same exact process to find our second derivative. We take the derivative of r prime. R prime over the magnitude of r prime, r double prime over the magnitude of r double prime are going to another couple of very important things that we're going to do with vector valued functions as we move forward when we start talking about the properties of curves in space. So when we start talking about acceleration, velocity, curvature, we're going to use these quantities quite a bit. So questions on derivatives. So what we're going to do is on Monday we'll talk about integrating vector value functions. We have a CML next Tuesday. And then we start talking about velocity and acceleration, tangent vectors and normal vectors. We're not going to have a quiz. The way it's set up right now, I don't have a quiz scheduled until the 23rd of January. So our quiz is a little ways out. I didn't think it made sense to do a quiz before that because we're just going to talk about a couple of sections. And we have a holiday in there also. We have a 3-day weekend in there as well. All right, questions today? Okay. No?
Some food will get erased from the And then you won't have to do it.